So it's Dr. Kate, and we'll just finish up the experimental design lecture, and this will go along with the handout that I gave you last time. So let's go. First thing I want to talk about are main versus interaction effects, and this is what we started to talk about at the very end last Wednesday. Now, main effect means that one independent variable will be enough to explain whatever is going on with the dependent variable measure, versus an interaction, which means that there is a combination of independent variables that explain what's going on with a dependent variable measure. And if you remember, we had the x crossing between the variables, and that's the interaction effect. Now, when you read literature, they might say there's a row effect, they might say there's a column effect, and those are main effects, and all that is looking at the table and seeing, is it going across horizontally or is it going vertically, whatever the significant effect is. So I was finding some examples here and there, which is what I was trying to put together for you that we'll get into. Now, if you look at this table, it's a 2 by 3 factorial design, which means there's one independent variable that has 2 values to it, which is gender, our favorite, and there's one independent variable with 3 values, which is type of treatment, and we're just saying A versus B versus C. Now, if we look across, meaning the row, there is no gender difference. And you can see that as the 27 for both male versus female. But if we look column-wise, we see treatment A results in some sort of a score of 30, treatment B 30, treatment C 20. So therefore there's the main effect of treatment, meaning that treatment C was significantly less successful than either treatment A or B, and it doesn't have any variation by gender. As you can see, they're the same versus male or female across the board. But if you just look at gender, you'll say, oh, there is no difference that way, but there is by type of treatment. Now, this one I got out of a textbook and it looked a little funky, but I wanted to show you a 2 by 2 by 2 table for a factorial design. And here they're looking at what media is used, and they're measuring within the boxes or cells the knowledge level on current events. So we've got possibilities of somebody reading a newspaper or not reading a newspaper, listening to radio, not listening to radio, listening to television, not listening to television, for news on current events. So you can see here how and why you need 8 cells for a 2 by 2 by 2. And you're going to take a look at all these different possibilities of what connects with what. Now, this is referring to the handout that I gave you, just a bunch of different examples of. First thing I want to point out is right under the table, the capital letter N. That means how many people are in this study here, part of this table total. So the capital N is the entire population. The small n, which equals 40 in this case, is how many people were within each cell. So we've got here a 2 by 2, which is gender of students, gender of teacher. and we're looking at the dependent variable of mean scores on a 100-point midterm exam. Now remember that the first thing to look at is the significance levels at the bottom. The interaction here in shorthand says gender by gender, which means gender of students by gender of teachers. And that P level of 0.69 is non-significant, so I'm not paying attention to that. The only significant result we see is gender of teacher, which has a P level of 0.01, which is less than the 0.05 threshold. And you can see the F equals 4.78, which is much higher than the other F values that you see, which is another clue. So if you look at the table itself, you can see gender of teacher, in this case, female teachers, students scored 80 on average for a midterm exam, and male teachers, students, regardless of their gender, scored 60. So, we would say there's a significant impact of the gender of the teacher and the score. Now, of course, there's a zillion other explanations we aren't taking a look at, but for simplicity's sake, we'd say for whatever reason, the female teachers, students score higher, significantly higher on the exam. Now here's the next table, which in this case is showing that the male teachers have students scoring significantly higher than the female teachers. So why I wanted to point this out is you get the exact same P level and F value for gender of teacher, but an opposite result. So you have to make sure you're reading what the tables are providing and not just looking at the P level, because maybe you predicted female teachers and you see, oh, I've got a P level that's significant, so I must be right. Well, in this case, the male teachers mean or average score on the exam was significantly higher than females. So you get the same actual statistical results, but opposite of what we just looked at with the male-female teacher slide earlier. This shows P levels that are all non-significant. So there would be nothing to actually talk about. NSD, no significant difference, is what that stands for. And you can see the male versus female average the same, 70 on that exam, and male versus female teacher, while the male teacher's average for their students is higher, it's not a statistically significant difference, and that's what we talk about. If it's not that, then there's nothing to say. Now here, again, look at the P levels. The interaction, non-significant. Gender of teacher, non-significant. Gender of students, significant. 01 level. And what do we find here? You look across the rows and you see female students in this case averaged an 80 versus males a 60. Therefore, female students scored significantly higher than male students. And it's a row effect. SD for the title, significant difference. And here we have an interaction effect. Gender by gender. 0.001 and the F equaling 2.8. So what do we see here? That there's an interaction between gender of teacher and gender of students for the overall result on this 100-point midterm exam. And if you look within, you see that male teachers with male students, that the students score higher with like gender teachers. Same with females. Or vice versa, that if you have a male teacher with a female student or a male student with a female teacher, they will score significantly lower than those with teachers of the same gender. So that's what it means, and that's what.
So now that we've gone through all of those examples, you are now assigned to your next task, which is to create a 2x2 factorial design. I encourage you to go back to what we just talked about, and you can use those as far as how to lay out this kind of a table. If you want to put this into an Excel file, that's fine. Or if you want to create a table within a Word document, do that as well. All you need to do is take one of your old research questions that you were working on. Your old questions where you said, what is the relationship between an IV and a DV, now needs to be altered so that you have a second independent variable. Each of your independent variables can only have two values to them to be a 2x2 factorial design. Recreate a table similar to what I've just shown you, and you're going to have one independent variable along the left-hand side, and the other will run across the top of your table. Unlike the tables we just looked at, there is no data, so you're not going to put any numbers inside. That part's going to be blank. So what do you have to do? Create the name of the table, so call it Table 1, and based upon what your research question happens to be, you then title the table. So a good idea would be write the research question first into what you're going to hand in. Next, create a name for the table, and remember that after the dependent variable, you see in my examples the word by, by, and what comes after by are the names of your two independent variables. And then just upload that into Canvas and I will take a look at it. Good luck, and we'll talk to you again.